Okay, so the last video we ended with the solvation or solution process where we dissolve calcium chloride and it dissociates into calcium ions and chloride ions. And the delta H that we calculated, it was a negative 80.9 kilojoules per mole. So we know that if we dissolve 1 mole of calcium chloride, we would be releasing 80.9 kilojoules of energy to the surroundings, right? Probably water, right? Because this is in solution. When you have a negative delta H, that tells you that this is an exothermic process, that energy is released to the surroundings. So what happens in a lot of chemical reactions is you have your energy over time, and you start the reaction with your reactants, right? And you have to always go uphill, right? You always have to put energy in, either, usually to break bonds, right? That destabilizes molecules, so you have to put energy into that. And then as you form new bonds, energy is released. And basically, depending on where you start, initial, versus where you end up, final, overall, that'll tell you whether you have an endothermic or exothermic process. Because where you end up in energy is lower than where you started, net, right, overall, you have a release of energy. And that means that your delta H is going to be negative, right? That shows you that you have an exothermic reaction whenever the sign of delta H is negative. And again, that's for the system. When the system is negative, that means the surroundings will be positive, right? Because remember, it's a transfer. So the system is going to have a loss of energy, and the surroundings is going to have a gain in energy. So when we did an exothermic reaction back in Intro Chem, we could feel the test tube getting warmer, right? And that's because the reaction that's taking place inside is releasing energy, right? Endothermic is the opposite, right? If we looked at our energy diagram over time, here we're going to start out at a certain energy level with our reactants. Again, always that uphill climb. But then as we release energy with forming new bonds, we don't release quite as much. So now what we look at is, okay, we started here and we ended up here. So overall, our delta H is going to absorb energy from the surroundings, which means our delta H is going to be positive, greater than 0. Like, we're going to have energy put into this in order for it to go. And so in this case, the system is absorbing energy, which means the surroundings is supplying that energy and losing energy. So my favorite example here is when we evaporate water, right? We know that in order to boil water, we have to put energy into it. We know that because we put the pot of water on the stove and turn on the heating element, right? And then that makes our water eventually come to a boil. But remember, that simple process is how we keep our body temperature cool. Because when we start to overheat, we sweat. And as that sweat evaporates, that particular system is endothermic. It absorbs heat from the surroundings. And of course, the surroundings are the molecules inside of our body, right? So that the surroundings, the chemical or the compounds and the molecules in our body, they supply that energy to this evaporation process. So the evaporation process is basically sucking out all our energy. So it keeps our body temperature cool, right? It keeps it right where it's supposed to be. So when we look at enthalpy of reaction, right, now we're going to start looking at enthalpy as another stoichiometric measurement or calculation that we can do. But this reaction here, we're taking oxygen and turning it into ozone. All right, and fortunately, that is, or not fortunately, but that is an endothermic process, right? Delta H greater than 0, so endothermic. All right, it's going to absorb energy from the surroundings. And we want to look, okay, well, what would that be if I had 3 half oxygens going to ozone? So this is going to be sort of a precursor to Hess's law when we look at it. And what we can look at is when you look at your delta H, it's based on this particular reaction. So if I have 285.4 kilojoules of energy absorbed, that would be for every 3 moles of O2, right? Or if I want to look at ozone, for 2 moles of ozone. And when I look at this equation, right, that I want to know the enthalpy for, what I notice is I have half as much. Instead of 2 ozones, I only have 1. And instead of 3 oxygens, I have 1.5. So if it takes 285.4 kilojoules for this reaction to occur, for 3 moles of oxygen to turn into 2 moles of ozone, if I'm going to do half that reaction, I'm going to need half that amount of energy. So what I'm going to just do here is the delta H for this reaction would be the 285.4 kilojoules divided by 2. So 285.4 divided by 2, that delta H would be 142.7 kilojoules. And again, that's written as 142.7 kilojoules for every 1 mole of ozone, or for every 1.5 moles of O2. So it's the same reaction, I just cut it in half, so my energy absorbed would be cut in half. Now, just as an aside, right, what if I swapped it, right? What if, question mark, instead I take that ozone and turn it into oxygen? So I'm doing the reverse reaction here. So it makes sense that if I absorb heat turning oxygen into ozone, I'm going to release heat turning ozone into oxygen. So if going from 3/2 oxygen to ozone absorbs 142.7 kilojoules, going from 1 ozone to 1.5 oxygens, I'm going to release 142.7 kilojoules. So something that'll come up in the next video is if I multiply or divide through a reaction by some number, I'm going to do the same thing to delta H. So I cut the reaction in half, so I cut the delta H in half. The second thing we learn is that if we reverse the reaction, then we're just going to reverse the sign on the delta H. And that made total sense to me, right? If I'm going to absorb energy going this way, then going the opposite way, I'm going to release it. All right, now when we look at it in terms of stoichiometry, we started seeing that here, that when we're given a delta H value, it applies to any substance in that reaction. This would be 285.4 kilojoules absorbed for every 2 moles of ozone made. So what is the enthalpy change when 12.8 grams of hydrogen reacts with excess chlorine to form HCl? All right, so we want to know enthalpy, right, which is our heat. And what we can see here is that we've got negative 184.6 kilojoules, right? That is our delta H value. That is the energy released when I react, based on how this is written, 1 mole for every 1 mole of H2. So when we look at our enthalpy, right, or H, or Q, if you want to leave it in heat, that's fine too. We have our negative 184.6 kilojoules per mole of H2. And just as an aside, if this had a coefficient of 2, then we would have a coefficient of 2 here. It's based on however the equation is written. So the negative 184.6 kilojoules is released for every 1 mole of hydrogen. Of course, that's what we put here. Well, we don't have a mole of hydrogen. We have 12.8 grams of hydrogen. So this is a conversion factor, right? And we can use the delta H for any substance we're looking at, hydrogen, chlorine, or HCl. In this case, we're looking at hydrogen, so that's why I wrote it in terms of hydrogen. So if I look at how much hydrogen I have 12.8 grams of H2. We know we always have to go to moles, right? That never changes. 2.02 grams of hydrogen is 1 mole of hydrogen. And then the enthalpy change, right? Negative 184.6 kilojoules for every 1 mole of H2 reacted. right? And that'll give us our energy. So 12.8 divided by 2.02 times a negative 184.6. So we get a negative 1,170 kilojoules, right? And so that is energy that is released when that 12.8 grams of hydrogen goes through the reaction as listed with excess chlorine. All right. All right, next page, another example. What volume of methane? Methane is CH4, so we want to know the volume of that. And we are at 25 degrees Celsius, and we are at 745 torr. Hopefully that is making you feel like this is a gas law problem. And we're going to burn that in excess oxygen, and we want to release 1 times 10 to the 6 kilojoules of heat. All right, so this is sort of like our A, right? This is what we want, right? This is our quantity, and we want to know how much methane to get there. So this is actually our starting measurement. We want to produce that much heat, right? And so it's being released. So we have a negative 1.00 times 10 to the 6 kilojoules of heat released. Looking at our delta H, it says negative 890.3 kilojoules of heat is released every time we react 1 mole of methane. And what I'm going to do is stop there. So I'm going to take my 1 times 10 to the 6 and divide it by the 890.3. Right, notice the negatives cancel out. All right, so I have an N of 1,020 moles of CH4. So 1,120 moles of CH4. So if 1 mole of methane releases 890 kilojoules, how many moles to release 1 times 10 to the 6 kilojoules? So we start with our energy measurement, use our enthalpy and relate it to moles of methane, because that's what we're looking at is the methane. So I get 890.3 kilojoules released for every 1 mole of methane. So then I need 1123 moles of methane. I just rounded it to 1120, but we can round it at the end if you want. Keep it as 1123. Now I have N, and the reason why I talked about N is because I could tell this was going to be a Pivnert problem, right? Because we're looking at a gas, we've got temperature, pressure, we know then that it's going to be a gas loss problem. So temperature, just really quick, make sure it's in Kelvin, so 298 Kelvin. Pressure in ATM, so 745 divided by 760, I get 0.980 atmospheres. And now I'm ready. So volume would be N, 1123 moles, R, 0.08, 206, temperature of 298, and our pressure of 0.980 atmospheres. So taking my moles times my R times temperature, and then divide that by 0.980 atmospheres, keeping 3 significant figures. Ooh, okay, 28022 would be in liters. I'm just going to type it in one more time just to make sure I didn't mess anything up. Alright, and so then in order to get this into 3 significant figures, I'm going to have to use scientific notation. 2.80 times 10 to the 1, 2, 3, 4 liters. That would be my volume of methane I would need to produce 1 times 10 to the 6 kilojoules of heat, right, to release that much heat. All right, and then, so on this one, again, just kind of going over it again, when you have the enthalpy of a reaction, that tells you the energy, in this case, released. If it were positive, it would be absorbed by this reaction. We know combustion reactions produce energy, right? So this is the combustion of methane. So I get 890.3 kilojoules released for every 1 mole of methane. So if I want to know the volume of methane, this is going to act like my B, and my heat, right, is going to be my A, my starting point. I want to produce 1 times 10 to the 6 kilojoules. I know 1 mole gives me 890.3, so I would need 1123 moles of methane. Then because it's a gas, and this is a gas loss problem, I use Pivnert. I've got my moles, R, temperature in Kelvin, pressure in atmospheres, that'll tell me my volume of methane that I need to produce that 1 × 10⁶ kilojoules of heat. All right. One other question here. We've got what volume of HCl gas, so again, a gas law problem. We're at 125 degrees Celsius, so that'd be 398 Kelvin, and a pressure of 0.971 atmospheres. And it says, what volume of HCl would be produced if 1575 kilojoules of heat was released in this reaction? So again, it was released, so negative 1575 kilojoules. That's the energy that's released. Looking at my enthalpy of the reaction, I get 185 kilojoules released for every 2 moles of HCl, right? Because we're comparing it to HCl, and that has a coefficient of 2. So just like we saw before, this is a gas law problem. That's going to give me my moles. So I get 185 kilojoules released for every 2 moles of HCl. So how many moles do I need to get 1575? So I'll take my 1575, divide by 185, but then times 2, because I need 2 moles of HCl for every reaction. So I have 17.0 moles of HCl. Now for the Pivnert, volume would be my moles, 17.0 times R, 0.08206, temperature in Kelvin, 398, divide by pressure in ATM, 0.971. So what volume of HCl would be produced? I get an answer here in liters to 3 significant figures of 573 liters. So that would be my volume of HCl produced when I've released 1575 kilojoules. So your heat is acting like a mass or a volume. It's a measurement, right? But in order to relate that in the stoichiometry, this is acting like a stoichiometric conversion factor. So if we had mass, we use molar mass. If we have volume of a solution, we use molarity. If we have heat, then we use the enthalpy. And that enthalpy that's listed is always based on how the equation is written. So it depends on what substance you're looking at. Since we're looking at HCl, that delta H is for every 2 moles of HCl, right? If I were just looking at chlorine, it would be 1 mole of chlorine or 1 mole of hydrogen. But since we're looking at HCl, it's this much energy for every 2 moles of HCl. So I take the energy that I've released, divide it by my enthalpy of 185, and times it by 2 to get my moles of HCl. And then when I plug that into PV equals nRT, I can figure out my volume that I need. So, or sorry, in this case that I would produce since it's on the product side. So when I make this amount of energy of 1575 kilojoules released, I have produced 573 liters of HCl. All right, that will be a good place for me to stop for this video.